Let's first, however, see an example of when things go right using the ratio test, and let's walk through the very prescriptive methodology we're going to use to apply the ratio test. So let's use the ratio test to study this series that we have written up on the screen right here. Quantity n plus 1 times quantity n plus 2 all over n factorial. Following blindly, we feel like the ratio test is a good thing to use for this particular series because we've got a factorial there. So let's take a look at the steps we need to perform in order to complete the ratio test every time. The first step is to determine the absolute value of the n plus first term. So what we do in order to compute the absolute value of the n plus first term is everywhere we see an n in this expression, we add parentheses and we write n plus 1 instead. Now the reason for those parentheses is that it is very easy to make computational and distributive mistakes when doing the ratio test, and so adding this extra set of parentheses is going to hopefully help us prevent some of those mistakes. So all that I have written down right here, as nasty as it looks, is just an n plus 1 plugged in everywhere that you see an n up here. After using our parentheses in order to be extremely cautious, we can simplify this arithmetic and see that what we have is quantity n plus 2 times quantity n plus 3, all divided by quantity n plus 1 factorial. Now you'll notice that I haven't put absolute value signs anywhere, but I haven't put absolute value signs anywhere in this expression because they're entirely unnecessary. My n's start at 1 and go off towards infinity, and each of these individual terms is going to be a positive value when n is a number that's at least 1. So my absolute value signs here are entirely unnecessary, but in theory, in future examples, they may not be. The second step is very similar to the first step, but a whole lot easier. Determine the absolute value of the nth term. Here, there's nothing to do in this step other than to rewrite the general form of the addends from up here down here. Again, in theory, we might have had to think about the absolute value of each of these terms, and then there might have been something to do at this step, but because all of our terms happen to be positive, there's no further action to take in this example. Now, the third step before I take any limits is to simplify the ratio of the absolute value of my n plus first term to the absolute value of my nth term. So what we do is, taking our answers from step 1 and step 2, we plug them in to this monumental fraction right here. That's a very messy thing to consider, so our first step is to rewrite it as my numerator right here, multiplied by the reciprocal of my denominator right here, and then comes the absolute best part of the ratio test, which is the simplifying process. So the goal at this particular stage is to identify as much as possible right here in these fractions being multiplied to cancel. Now factorials come up a lot in the ratio test, and the trick that we want to use with factorials when they appear in the ratio test so that we can notice the canceling is to use a trick we've seen before, which is when we have something like n plus 1 factorial, we can rewrite that as n plus 1 times n minus 1 times n minus 2, and so on. And the n plus 1 is sort of a first term, and then what's left after that is n times n minus 1 times n minus 2, and so on. In other words, right after that n plus 1, we're multiplying by n factorial. So we can rewrite that n plus 1 factorial as the quantity n plus 1 multiplied by n factorial. And then this is the stage where I would get very happy and I would get out my red pen and highlight all of the things that are going to cancel. Here I have an n plus 2 in the numerator, and over here I have an n plus 2 in the denominator. These two terms will cancel. Similarly, I have an n factorial in the numerator over here and an n factorial in the denominator over here. These two terms should cancel. Once I've done all of that canceling, this expression becomes a lot easier than it looked initially. It simplifies down all the way to n plus 3 divided by the quantity n plus 1 squared. That simplification is absolutely necessary because the fourth step is to now take the limit of that expression as n is going to infinity. It's that value that is ultimately my ratio rho. In taking that limit as n approaches infinity of this thing that we simplified in the previous step is much nicer looking than it would have been at this stage. Now when we're asked to take this limit, we can determine it through many different means. One of those mechanisms would be to check that this limit is an indeterminate form and apply L'Hopital's rule. Another method is to think about rate of growth, where I have a linear function in the numerator and a quadratic function in the denominator. The quadratic function grows faster than the linear function, and therefore this limit is 0. The fifth step is a real quick step where we take a look at the value of that rho and just say, which case do we fall in? Do I have a number less than 1, bigger than 1, or equal to 1? In this example, I've got a 0 as my rho value, and because 0 is a number that's less than 1, we can apply our ratio test to determine that this infinite series is a convergent one.